Welcome to The Explainer. Today, we're taking a deep dive into mastering the physics of work, energy, and power. We're going to build your ultimate exam success blueprint, looking exactly at how to navigate those tricky questions and truly master these fundamental concepts without losing any unnecessary marks.
Here's our game plan for today. We're going to cover the physics of work, carefully sidestep the parallel force trap, define the strict limits of energy and efficiency, balance potential against kinetic energy, and finally, master power equations. Let's get right into it.
Kicking things off with Section 1, the physics of work, and why having precise definitions is absolutely crucial for scoring maximum marks.
Now, the text explicitly warns us that we have to be super careful with this term. In physics, work is defined as being done when a force moves its point of application in the direction in which the force acts. You can't just write force times distance on an exam. That's going to lose you marks because it completely ignores the direction. Think about it. 1 joule of work is strictly 1 newton moving 1 meter in the exact direction of the force. Period.
And here's the critical rule to remember. Both force and displacement are vectors. What does that mean for us? Well, for work to actually be done, there has to be a component of the force that is strictly parallel to the displacement. It's all about direction. Since vector quantities inherently possess both magnitude and direction, alignment is everything.
Moving right along to Section 2, the parallel force trap. Let's explore exactly how examiners use this vector rule to trick you and why simply multiplying the biggest numbers on the page is a guaranteed fail.
Okay, this image perfectly exposes the trap. Look at the child going down the slide. They move a total distance of 5.0 meters, right? But here's the catch. Gravity is acting vertically downwards. So you only calculate work using that parallel 3.0 meter vertical displacement. If you just grab the biggest numbers and multiply the 250 Newton rate by the 5.0 meter slide length, boom, wrong answer. You absolutely have to link the specific force to its parallel displacement. So the correct calculation here is 250 newtons multiplied by 3.0 meters.
Now, what happens when things aren't lined up perfectly? This illustrates it brilliantly. Imagine a guy pushing a wheelbarrow at a 75-degree angle. You don't want the vertical force just shoving the wheel down into the mud, right? Instead, you have to use a bit of trigonometry to resolve the vector and find the horizontal component that's actually pushing the barrow forward.
So how do we solve these consistently without panicking? Just follow these exact steps. First, resolve the force into a horizontal component using cosine, or f cos theta. Then, isolate that parallel component and multiply that specific horizontal force by your displacement. That gives you the final equation. Work done equals F times displacement times cos theta. Actually, a pro tip here. Write your answer using clear numbered steps on the exam. Show the examiner exactly how you resolved the force before doing the final calculation. It practically guarantees maximum marks.
Let's jump straight into Section 3, Energy and Efficiency Limits, where we look at total input versus useful output and why machines are literally never 100% efficient.
It is so important to distinguish between your useful energy output and your total energy input. If an exam asks you why the total input is always greater, the precise, undeniable answer is that machines are never 100% efficient. While they're running, some of that total input energy invariably gets converted into unwanted transient forms. Usually that's thermal energy or heat caused by friction. So your useful output is always just a fraction of the total.
I love this part of the source material. Here is a massive study tip directly from the text. What happens inside the motor is complex. This is not needed for the exam and will not get you any marks. Listen, do not waste your precious exam time writing a novel about the complex energy forms bouncing around inside a motor. It won't get you a single extra point. Just stick to exactly what the question demands.
All of this, of course, ties right back to the granddaddy of them all, the law of conservation of energy. It states that the total energy of a closed system is constant. Energy cannot be created, it cannot be destroyed, it just changes outfits, converting from one form to another. Remember, closed system literally means nothing gets in and nothing gets out. So when you're calculating efficiency, you're not finding lost energy. You're just tracking energy that turned into something useless for your purposes, like sound or heat. The total joules, they stay exactly the same. All right, on to Section 4, Potential versus Kinetic Energy. Time to master the physics of motion and position.
Let's look at how these formulas are actually built. It's kind of like a logical puzzle. We start with the basic work equation, W equals F times S. Then, we substitute force with Newton's second law, F equals ma.
Next, we apply the equation of motion for an object starting from rest. That's v squared equals 2as. We substitute that in to get work equals mass times v squared over 2, and once the dust settles from the math, we are left with the beautiful, perfect formula for kinetic energy, 1/2 mv squared.
You can see this formula in action right here with the text's catapult example, calculating the kinetic energy of a flying pebble. But hey, warning, watch out for the classic examiner trap here, units. Seriously, they'll try to trip you up. If a question says a cricketer bowls a 160-gram ball at 120 kilometers per hour, you cannot just plug those numbers in. You have to convert the mass to kilograms and the speed to meters per second first. Only then will you get the correct answer of 89 joules.
Now, I've got a question for you. How do examiners test your practical, physical lab skills when you're calculating gravitational potential energy? Think about it. If you just write down, "Oh, I'll use a ruler to measure the height," you are going to lose marks. Why? Because physics demands absolute precision.
The text specifically flags this. You need to explicitly state that you would use a set square. Why? Because a ruler on its own can easily be tilted, which means you'd be measuring the hypotenuse, not the true vertical change in height. Writing down that you'd use a set square proves to the examiner that you truly understand the physical constraints of aiming for absolute accuracy in a real lab environment.
Finally, we have Section 5, Mastering Power Equations, looking at the rate of doing work. By definition, power is simply the rate of doing work, or the rate of transforming energy, measured in watts. 1 watt equals exactly 1 joule transferred per second. Now, here's a linguistic tip. In physics, whenever you see or use the word rate, it inherently means divided by time. So please don't write the rate of work done per unit time. That's totally redundant. Just firmly state, power is the rate of doing work.
And check this out. This slide illustrates the literal exam cheat code. We know power is work over time, and work is force times displacement. Well, if you replace displacement over time with velocity, look what happens. You derive the super elegant shortcut P equals FV. Power equals force times velocity. This is an absolute lifesaver for objects moving at a constant speed.
The text demonstrates this beautifully with a cyclist. First things first, convert that 27 kilometers per hour into 7.5 meters per second. Always check your units. Then, just apply the P equals FV shortcut. Multiply the frictional force, which is 50 newtons here, by that velocity, and boom, you instantly get 375 watts. Maximum marks secured efficiently, and you didn't even have to hunt for a time variable because you bypassed it completely.
And wait, the text gives us another amazing shortcut. Let's say a question gives you power values instead of energy values. You can calculate machine efficiency strictly by dividing the useful power output by the total power input. Think about it. Since power is just energy per second, the mathematical ratio is exactly the same. This little trick alone can save you so many valuable minutes on a complicated, multi-part question.
So, armed with these precise definitions and proven shortcuts, are you ready to navigate those tricky exam questions and lock in your target grade? We've tackled the exact physics of work, completely sidestepped that nasty parallel force trap, and unlocked some seriously powerful shortcuts for energy and power. The next time you sit down with a complex physics scenario, ask yourself, am I just mindlessly crunching numbers, or am I truly analyzing the physical system in front of me? Keep studying smart, keep analyzing, and I'll see you in the next explainer.